Let's look at the first of our three generalisations to the simple functional. So we've seen before that the simple functional that we've been using throughout the course is of the form f of our independent variable x, and we would have a function of x, so we'll just say the function's y of x, and we would have the derivative of that as well. So this here would be our simple functional. And we've got one independent variable, which is x. Now if we were integrating this between the limits x0 and x1 by dx, the equation would be in this form here. Now in this simple functional, as I've said, the independent variable here is x, and we've got one function of x and one function which is the derivative of that. But we could have it where we have not just one function of x, we could have multiple functions of x. So for example, we could have y1 of x, y2 of x, y3 of x, and so on and so forth. And we could have y1 derivative of x, y2 derivative of x, y3 derivative of x, so on and so forth. So we could generalise this simple functional by adding in multiple independent functions of x. And that's what we've done with this generalisation here. Now the first thing to note is that we've replaced the independent variable x by the independent variable time. So rather than x, we've used time. Now the only reason why we've done that is because the example that we're looking at here is what we would see in a lot of examples in basic mechanics. And in basic mechanics, the independent variable would usually be time. So that's why we've replaced this with our time. But we didn't need to do that. We could have just kept it as a value of x if we wanted to. Now the other thing to note here is that the functions here, y1 of x, y2 of x, y3 of x, we've replaced these with q1 and q2, so we could have q1 of x, q2 of x, q3 of x. So these are our multiple independent functions, and we're going to have our q1 derivative of x, q2 derivative of x, and so on and so forth. So the reason why we use the value q is that, again, in mechanics, the value q tends to be used for generalised coordinates. So this is our first of our three generalisations. We have one independent variable, but we've got multiple independent functions. Now the way we deal with this is quite straightforward, and that is that we work through the Euler-Lagrange equation, so the derivation of the Euler-Lagrange equation for each of the independent functions. So really we're just doing the Euler-Lagrange equation. In this case here, their example is q1 and q2, so we're doing the Euler-Lagrange equation twice. If we had a q3, we would do the Euler-Lagrange equation 3 times, and so on and so forth. So the first derivation of the Euler-Lagrange equation, we've shown part of it here. So if you're unsure, you can always have a look at the derivation of the Euler-Lagrange in a previous video. So we could have the extremum here, I, and we can look at the change in the extremum. So this is going to be delta I1, and it's going to be the integral from t0 to t1 by dt, and we differentiate the functional here with respect to epsilon 1. So our epsilon 1 here is what we use in order to add on the variation. So we'd have to use the chain rule for differentiation. So we had our partial f by partial q1 by partial epsilon 1. And again for the partial f by partial q1 dash times partial q1 dash by partial epsilon 1. So again, we've seen this whenever we looked at the derivation of the Euler-Lagrange. And we can replace this partial q1 by partial epsilon 1 with our eta 1, and this one term here can get replaced with our eta 1 dash. Now what we would have done at this point here is we'd have worked on our integration by parts in order to get rid of the eta 1 derivative. and then we could have taken out the common factor, which is eta 1, and the eta 1 is our variation, and we know that doesn't go to 0, so whatever would be left inside the bracket would be the quantity that would equal 0, and that would be the Euler-Lagrange equation. So this is the Euler-Lagrange equation for the first value here, Q1. But we can also do it for the value over Q2 as well, and I've done that down here. So we're doing the same process here for deriving the Euler-Lagrange equation, but we're doing it for our value of Q2. And we've also got our variation, which has been created by our epsilon 2, but now we can make our epsilon 1 equal epsilon 2, and we'll have these two Euler-Lagrange equations. Now, there's nothing magical about anything we've done here. We've seen this very example whenever we looked at the equations of motion of a ball falling under the force of gravity, and we looked at the motion in terms of an x component, and we could look at the motion in terms of a y component, and we did that in the first video series. So all we're going to do here is extend this to n coordinates. So instead of having Q1, Q2, Q3, it goes off to infinity. So we can say that if the integral from t0 to t1 of our function of an independent variable t and our functions qn and qn dash by dt is stationary for weak extremums, then we can write out this general form for our Euler-Lagrange equation, and we're just replacing our q1, q2 with the values qn and qn dash, where n is equal to 0, 1, 2, 3. Okay, so that's relatively straightforward. So let's go ahead and we'll look at this example here, and we'll look at it in terms of our second variation and also our conjugate points. So thank you for listening. I'll get you on the next video. Goodbye.